So part 2 of the last new lesson I will ever teach you. We are talking now about the conditions for getting to perform this inference, so this linear regression model. We'd like to apply it to a population. We've got a super cool acronym of LINER to help you remember all of them because there's a lot of conditions for this one. It's a bit different from the ones we had been doing. So if you have an observation of your explanatory variable x and the response variable y, if you're trying to study or predict the behavior of y for given values of x, the first thing you need is a linear relationship. If it's not linear, you're not going to be doing much with that. There are 2 ways to actually check for linearity, which apparently I'll get to in a second because it's not on here. So the actual relationship between x and y is linear. So for any fixed value of x, the mean response, mu sub y, falls on the population regression line, the mu sub y equals alpha plus beta x. You do need to have independent observations. So the individual observations are independent of each other. You can always check with a 10% condition if it was sampled without replacement from a greater population. You need to have normality. So for any fixed value of x, the response variable y varies according to a normal distribution. So we'll talk about how we can check that in a second. Then we need all of those normal distributions to have equal standard deviations. Now you're probably not going to have multiple observations you're going to check this, so we'll check this a particular way. So the standard deviation of y, sigma in this case, is the same for all the values of x. This is what we were looking at earlier where they were all 6. And lastly, the one that we are used to, we still need randomness. If you have a convenient sample, this will not apply very well to your population. So the data has to come from a random sample from the population of interest, or it needs to be a randomized experiment, but something's got to be random. So it's not really hard to check for major violations. We're not going to get super caught up in the details, but most of your conditions are going to involve this population regression line and the deviation of responses from this line. Now, you usually can't observe the population line, but we can talk about the regression line that estimates it, so the sample regression. The residuals from the sample regression line estimate the deviations from the population line. So we've talked about residuals. These are estimates of the population because that's what samples are always supposed to be. So we check several of the conditions for regression inference by looking at the graphs of the residuals. So it says start by making a residual plot, a histogram, dot plot, stem plot, or box plot of the residuals. I'm pretty sure most of the examples I'm going to be giving you, these are done for you, so that shouldn't be a huge time crunch that you're going to have to deal with. So if you're just trying to check for linearity, we did that back in, I think it was Unit 3. Basically, you look at your scatter plot. So you sketch the x values and the y values, and you look for some linear relationship. You're hoping to not see any type of curve. So if you see something that looks like this, you're not going to be modeling it very well with a line. Also, you need to look for the residual plots. So when the residual plot's given to you, you just want to look for no pattern at all. So this is an example of something that's bad. So the residual plot is clearly showing some curved pattern here. When you see some curved pattern, that means that your data is not linear. There's some underlying pattern that's not a linear pattern. So that's how you check for linearity. We've done that before. For the independent condition, knowing the value of the response variable for one individual should not help you make any predictions for the response variable for other individuals. We've checked our 10% condition before. You could do that. There technically are other issues that could cause lack of independence. We're not going to get into this, but theoretically, if you measure a girl's height at age 6, it's going to help you predict her height at age 7. So that is an issue. It's called, time series data. We're not doing that, but theoretically it's something you should know. So then the N in our LINER acronym is normality. This is when you need to be looking at a histogram, a dot plot, a stem plot, or a box plot of the residuals. And then you're looking for the same thing we've looked at before for normality. Again, it's not the whole population, but if you don't really see any strong skewness, if you don't see any outliers in that data, you're probably pulling from a normal population of some sort. So ideally, we would like to check the normality of the residuals of every possible value of x. You're rarely going to ever have that, so we're just going to make a graph of all the residuals to check for normality. It's the best we can do. For the equal standard deviation condition, this is when we need to look at the scatter plot of the residuals, and really we're looking for what happens around the residual equals 0 line. So you're looking at this horizontal line, which if it's a residual of 0, residual is your distance from the regression equation. So if you're on that, you don't vary at all. You actually match your predicted value. What you want to see is that your graph of the residuals have equal variability at all x values. So the example of a bad one, the y has greater variability for large values of the explanatory value of x. As you go down to bigger x values, you have more variability. When you're down at the smaller values of x, there's small variability. You would like to see about the same all over the graph. That's what the equal standard deviation check looks like. So look at your residuals, compare it to this baseline of this horizontal line, and essentially you don't want to see this like trumpeting out shape. That's bad. And randomness, we've done this before. Make sure it says something about a random sample, a randomized experiment. That's not new. So an example of checking all of this fun stuff. Miss Barrett's class did a fun experiment using paper helicopters, which honestly, I'm curious how you make a helicopter out of paper, but that's neither here nor there. After making 70 helicopters using the same template, students randomly assigned 14 helicopters to each of 5 drop heights. So we've got these different heights that they're being dropped from. Teams of students released the 70 helicopters in random order, measure the flight times in seconds, and then they used computer software to create least squares regression, and then they did analysis for these data. Here are the scatter plot, which is this first one, the residual plot, and a histogram for the residuals. That's what we're going to use to check for our conditions for inference. So, linearity. There are 2 places you check for linearity. You check your actual scatter plot of the data, and you check your residual plot. Scatter plot, you would like to see some type of line. Residual plot, you just don't want to see any type of discernible curved pattern. So what we see is that the scatter plot shows a clear linear form. Yes, they're kind of grouped. They're like stacks, but that's not really a problem here. So we see this increasing slope to it. So our scatter plot shows, I'm just going to put a clear linear form. But when we look at the residual plots, there's not really any curve here. We just kind of see a bunch of dots everywhere, some above, some below. It's not following any pattern. So I'm just going to put no leftover curved pattern in the residual plot. So we've met the linearity condition. To check for independence, because the helicopters were released in a random order, we don't have any helicopter used twice, so we're not going to be able to use one result to make predictions for another observation. That's really how we know we have independence. So we're not checking the 10% condition. There was no random sampling. We don't have a population of helicopters from which we selected a smaller sample. So I'm not checking the 10% condition. I'm just making sure that there's no way that one outcome helps me make predictions for the next. So I'm going to say because the helicopters were released in a random order, and no helicopter was used twice, knowing the result of one observation should not help us predict the values of another observation. We would like normality. We have to have that for this inference to work. So we need to not look at the first 2 graphs. Now we need to look at any type of graph of our residuals, whether that is a scatter plot, or not a scatter plot, I can't even think about the list now. It's after 9 o'clock. I don't think well after 9. We need to look at, there it is, histogram, dot plot, stem plot, box plot. We need to look at some layout of our residuals, which is what this last one is. We have this histogram. This histogram is pretty normal shaped itself. Not perfect, but it's never going to be perfect. We're not going to get too, we're not going to overreact to any minor issues that we might see. What I see specifically, though, is there are definitely no outliers here, and we don't really have any strong skewness in any one direction. So that's what I'm going to note. There is no strong skewness. There's no outliers in the histogram of our residuals. Done. For the equal standard deviation, we need to look at our residual plot. Remember, this is where we're basically looking, is it equally laid out at all your values of x? So I'm going to go back to my residual plot, and I'm going to consider this center baseline of 0. I want to make sure that there's not more variability for the small x's. There's not more variability for the big x's. I don't want that fanning out shape to show up. And pretty much this is the same as this. This is the same as this. Now, to be fair, at the x value of 300, this is more spread out than the rest of them are, but that's not really enough to be a concern. Again, we're not going to overreact to minor issues. For the most part, we're not seeing any type of dramatic difference in the variability for different x values. So I'm just going to put the residual plot shows a similar amount of scatter about that horizontal line. So when we looked at it for each drop height for each x value, we saw a similar amount of scatter around it. I did note that flight time seemed to vary a little more at the 307 mark, but whatever, we're not going to care about that. And then randomness, I didn't bother leaving any blanks for this because it's always the same check. It said the helicopters were randomly assigned for the 5 possible drop heights, so we're good. Once you check your conditions, we can make estimates. Specifically, we're going to be estimating our population, the true slope beta. We could do others, but this is the one that mostly is of concern. So the least squared regression line computed from the sample data estimates the population regression line. The residuals estimate how much y varies about the population line. So sigma is the standard deviation of responses, so of all the responses about the regression. We can estimate it with the sample standard deviation of residuals. So this is our value of S. The formula for this is the square root of the sum of the residuals that have been squared. We square them so we don't end up summing to 0. And then we're going to divide this time by n minus 2. That's in this book, it just keeps saying this is beyond the scope of this course to talk about why it's n minus 2, but it's n minus 2. It's complicated. We're not going there. So we can think of this instead as the square root of the sum of each particular y value's distance from the predicted y value. So again, this is just us saying a residual. The actual value minus the predicted value. So this is the size of a typical prediction error. That's what S is. It's an estimate because it's from our sample data. So sometimes it's called the regression standard error. Sometimes it's called the root mean squared error. So as long as your conditions are met, the sampling distribution of the slope B is approximately normal with a mean mu sub B beta and a standard deviation that we already had that formula. We're not going to know sigma. It's very, very, very rare, because if we knew it, we wouldn't be doing all these estimates because we have our population information. So because we're not going to know sigma, we're going to have to estimate it with our value for S. S is our best estimate for sigma. Because you're not going to know the standard deviation either of S of X, you're not going to know all your population X values more than likely. We're going to replace it with sigma sub X. And again, for reasons we're not going to get into because I don't know them because it's not in our textbook, we're going to multiply that by the square root of n minus 1 instead of just the square root of n. So we're going to estimate the variability of our sampling distribution of sample slopes with the standard error of the slope. So our formula for that is going to be that value of s divided by s sub x square root of n minus 1. So the standard error has the same interpretation of the standard error of x bar or the standard error of p hat. So we always talk about these standard errors the same. It's how far our estimate typically varies from the truth. It's how far the sample slope varies from the population slope if we repeated the data production process lots of times. So although we give a formula for the standard error of b, so I just wrote out all this formula for b, you're pretty much never going to have to calculate it by hand. The computer output that calculates a lot of things for us will also calculate the standard error for us, and that's really, 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 really nice. It's going to be to the right of the sample slope b. So to look at what this looks like on an output, Ms. Barrett's class used computer software to look at the least squared regression analysis of their helicopter data. So this came from dropping 70 paper helicopters from these heights, measuring the flight time in seconds, and then they got this regression analysis here. So the conditions for performing the inference were already met, so we could go ahead and talk about the estimate for alpha. Now remember, alpha is the Greek symbol for A, and when we talked about, I'll write it over here, when we talked about coming up with our sample regression equation, we used y hat equals a plus bx. A is the constant. A is going to be your y-intercept. So I don't know the population y-intercept, but we can estimate it with the sample y-intercept. So I'm going to look at the sample regression analysis. I'm going to find my constant A, and we find our constant. It will a lot of times say the word constant. The coefficient of the constant, which just means the constant itself, is this negative value. So I'm going to say I don't know alpha. My best guess is that it's A, is that it's negative 0.03761. We are supposed to interpret this value. This is a y-intercept. So if you remember back to Algebra 1, this is where you cross the y-axis when x is 0. So in context, this would be if your helicopter is dropped from 0 centimeters, because we're saying x is 0, the height is 0, it's going to take negative 0.03761 seconds to land on average. Now, clearly unrealistic. We're extrapolating to this value, so a lot of times the y-intercept doesn't really make in context sense, but this is still what the interpretation is meaning, so that's what I'm going to write out. So if a helicopter is dropped from 0 centimeters, so an x value of 0, it will land, it will take negative about 4/100ths of a second to land. Now, I'm going to put, this is what it's going to take on average. Remember when we talk about our population, the slope, the y-intercept is average flight times for this, not the actual flight times. You could also talk about the predicted flight time, but most of the time when we're talking about our population, we're going to go with the average. So I can also estimate beta. Remember, beta is a Greek symbol for b, so this is our slope. So I still want the coefficient, but now I want the coefficient of our x values. We said that the x values was our drop height. So the coefficient of our x is this, therefore our sample slope is that, and that's our best guess at our population slope. It is our point estimate. So b is 0.005724. Now, slope is always, remember, change in y over change in x. We have to put this in context. It said that, we've said several times, that our height was our explanatory variable, and the flight time is what we're predicting. It's our y value. So change in y and change of x is change in flight time every time you change the height by an inch. So this is how much we are predicting the average to change. So I'm going to put that the actual flight times nope, that's not what I'm going to put. I'm on the wrong line. I need to actually go with what I said a second ago. So for each increase of 1 x value, so of 1 centimeter in drop height, the response variable, so the average flight time, the predicted flight time, the average flight time, it's a positive value, so in this case it's increasing. Not much, but we're predicting it's going to increase 0.005724 seconds longer. I would like to estimate sigma. Now I don't know sigma, so we have to go with S. So this is stated for us right here, the standard deviation of our residuals. So not the standard deviation of all the values given to us, but so it was 0.168181. So I'm talking about the residuals. The actual flight times are not all the same, so they're varying. I should say typically varies. By about 168.181 seconds. And when we talk about the standard deviation, the residuals, we're talking about how far it varies, not from the mean, but how far it varies from what we are predicting it to be. So, what did I just write? That many seconds from what we predict from our regression equation. And I'm just putting in context this particular least squared regression where I've defined the x value as our drop height. So the last thing we're supposed to find is the standard error of the slope. This is that formula that I told you you don't need to calculate because it's on your paper somewhere. So this, again, it says here standard error coefficient. We are finding the standard error of the slope, so not of the constant, but where we found our slope. It's right next to your slope. That's what we wrote. It is immediately to the right of the sample slope B. That's this 0.0002 value. So I'm just going to put the standard error of our sampling distribution of sample slopes, 0.000 2018. So if we repeated this sampling process lots of times, the slope of our sample regression line. This is how far our sample would typically vary from the true slope. Okay, so we again are planning to do inference for the population regression line. Yeah, actually I think I'm just gonna leave it at that. This is what all these values are.